Alright, time with math. Easy solution. We're going to discuss intro to differentials. Basically, showed in my earlier video, linear approximation. But now we're going to formulate it into dx and dy notation. That's basically what differentials are. Just these. Basically, I showed my earlier video on linear approximation is if you have just a random curve like this. This is x. This is y. So if you just draw a random curve, let's call this f of x. And then it's basically to approximate values close to, let's say, a known value at a. This is just f of a. All we do is draw a tangent line to it and get the equation of it. We'll call this L of x. And that's a linear approximation, and this one is equal to f prime of a. Yeah, it's f prime of a x minus a plus f of a. So that's this equation of it. And then for values close to it, let's say here, it's roughly close to here, but it gets further out as you get away from a. So basically that's linear approximation, but now we're gonna use dx dy notation, which is used a lot in math. So what I mean by this is, well, let's just start off with, if you let y is equal to a function of x, or f of x, then, and let's say you have it's defined d of x is a differential. Yeah, just a notation. It's a differential and it's an independent variable. Independent, so it could be any value. And so then, by definition, we're gonna define dy. So dy is equal to basically f prime of x times by d of x. So this is a dependent variable. So it's dependent on d of x. So dependent on d of x and x in this case. And if d of x is not 0, so if d of x isn't 0, we'll just write if. Then if you divide both sides by d of x, you're going to get dy over dx is equal to f prime of x. And that's just, we're used to this is a notation of the derivative. So that's all it is, but we're going to shift this over there, so we're going to solve for dy. So now, to see a geometric visualization of what I mean by this is, let's just write it over here. Let's draw a curve again, like, so there's xy curve. So let's just draw a curve like that, and we'll call this y is equal to f of x. And let's call this point P, and let's say we shift this by, this is at x, and we shift it to, let's say, here, where this is x plus delta x, or this thing is delta x from here to here, and we'll call this value here, we'll just call this s, and over here is q. These are the points, and this is delta y. And then if you draw a tangent line, let's just draw a tangent line across, like, we'll just change this curve a bit. Yeah, so I just changed it so we can draw a better line across from here. Yeah, so there's a tangent line across from there, and this value here, this we'll call this one, yeah, we'll call this r. So the p, q, r, s, and whatnot. So basically, so this is delta y. This is actually just dy, our differential. Like, because as you can see, this is just an equation of a line. This is the equation of the line with slope, which is the slope at this point right here. And from the curve, the point P, this one is just at, well, this is just, the coordinates are just x and f of x. And then at the point Q, this is x plus delta x. And then this is f of x plus, I mean f of x, it's inside, plus delta x. So that's the coordinates here, that's just fx here plus f of, and then the change in y in that drawing right there is just equal to f of x plus delta x subtracted by f of x. That's all it is. So now if we let, if we let delta x equal to d of x, just make it equal to the same thing. So this one is also equal to d of x, and then from here we know that, because well, we have this equation delta y, we would then have dy from our definition is just going to be equal to f prime at x times it by d of x. So then delta y represents, in this case, delta y represents change in, so the change in f of x. So that's all delta y is. This represents a change in, change in fx, and dy, which are differentially defined, is change in the tangent line. So it's a dy is the change of this line that we have that's tangent to f of x at this point here. So that's all it is here. So this one is just an approximation. That's all we're doing is changing the notation of differentials to get it of linear approximation in terms of this. So to illustrate this linear approximation notation with differentials, you can do an example here. So basically compare delta y and dy if y is equal to fx, x cubed plus x squared minus 2x plus 1, from x is 2 to x is 2.05 and x is 2 to x is 2.01, so it's a smaller change in x. So let's look at part A. Well, we know that delta y is just a change in these two values, so we'll just look at delta y is equal to f of f of 2.05 minus f of 2. And then you plug this in the calculator. We'll just get this over here. Alright, so we just type this one in here. F of 2.05 is just, let's go 2.05 cubed plus 2.05 squared minus 2 times 0.05 plus 1. This just equals 2. Just enter, and so 9.71625. Yes, I just wrote it down there, and then interchange this one with 2. Just delete these all. 2. This one is just equals 9. So then this would just equal 2. Well, 9 point that just 0.717625. So now let's look at the differential, the linear or the approximated values. dy is equal to, this is f of prime of x times dx. And in this one, we don't really need to use a calculator because this one is more complicated. We're not actually getting the exact value. So this one is just general formula for dy. So then f prime of x, we just write derivative of this. This is just going to be equal to, let's write it here, 3x x squared using power rule, 2x minus 2, and times dx. dx, remember, is just a change. If you saw the graph, all it is the change from x plus x minus x. So that's all this one is, dx. So we could just look at it here, and that's just 0.05. So this one is going to be 0.05. And remember, this one is at x is 2, because that's where we do our slope at x is 2. So we don't have to worry about 2.05 and whatnot there. So then we just plug in the values here. We're going to get 3 times, this one is 2 squared is 4 plus 4 minus 2. This is 12 plus 4, 16 minus 2 is 14. This is just 5 over 100. So is equal to 14 times 5 and 100. This one 5 times 4 is 20 plus a 2, 7, 5 times 1 is 7. So we have 70 over 100. And then this is equal to 0.7. And as you can compare, it's a bit off from there, but it's pretty close here. And this one we didn't actually have to use a calculator because we didn't. This one you could have done by hand, but it's just much longer. So so now let's look at part B. B is it's from, so let's look at delta y. This is from 2 to 2.01. So this one is equal to f of 2.01 minus f of 2. This one number we had it is 9. So I'm going to plug into this calculator again. This is 2 times 0.01. 0.0101. This one is 9.1407. (0701) minus 9. This just equals to 1.4071. And now if we look at the linear approximation, or dy again, this one is the same thing as above there, so we just write that same equation because we already did the derivative there. So it's going to be 3x squared plus 2x minus, what is that, minus 2. And then times by dx, and in this case, dx is 0.01. So this one, now we got to plug x as 2 again. This is the same thing, we already solved this one actually. Yeah, it's 14 there. So we didn't have to actually do that again. So this is just 14 times 0.01 over 100. And this is just equal to, actually, never mind, there's no 100 there, just 0.01. So all we do is divide by 100. This is just 0.14. And as you can see, it's getting closer and closer there. So this is roughly 0.14. And as you can see, this one is much easier to calculate. And sometimes it's actually impossible to solve y directly. So let's write that here. Yeah, so sometimes it's possible to solve it directly. And so then we actually need this differential. So this is actually required, is to approximate it using this method. And you can see this one is much easier than my linear approximation video. If you saw that, just using it this way is much easier. So then if you were to look at the equation, the linear approximation equation, which was just L of x is equal to f prime of a x minus a plus f of a. You could rewrite using differential. So with differentials, we could actually just write it as f of a plus dx is equal to f of a plus dy. Because this one would just be dx, and then this would be the derivative, and then dy is equal to, well, basically f of x dx. So this would be dx. So you could rewrite it like this way, and this is what's used more often. And then this one we could quickly approximate. Let's say if we had f of x is equal to, let's say, square root x plus 3, then dy is just equal to, well, just do derivative here. This is going to be 1 over 2 square root x plus 3 times by dx, and then at a is equal to 1, or the starting point, and delta x equals dx, let's say it's equal to 0.05, we could quickly get the equation. So f of 1 plus 0.05, yeah, this would just equal to, well, f of 1, yeah, f of 1 plus this one is 1 over 2 square root, well, 1 plus 3 times by d of x, which is 0.05. This value, if you put in a calculator, I could do that later, is this one's also 0.0125. And this one here, if you put 1 in here, that's, or 1 in here, this is just square root 4, that's just a 2. And then we get is equal to 2.0125. Let's do one more example just to illustrate how you could use it to solve for errors. This one's pretty useful. Let's got here. Let's say you had a sphere, and then you measured the radius to be, let's say, 21. Let's say r is equal to 21 centimeters. Well, that's what we measured, but then you have an error. Let's say possibly of, let's say, max 0.05 cm on this. So now the question is, what's your max error of volume? Let's say if you want to get volume, max error in volume. Okay, well, we know from this, we know that the volume is equal to 4 over 3 pi r cubed. So let's denote as the change in r, or the error, equal to dr. This is just error in radius. So then all we got to do is just use a differential linear approximation method we had to get now the error in, let's say, dv, or is equal to error in volume. And then this one is just going to be equal to dv is just equal to, well, v prime times by d of r, or radius there. And if you just take derivative of this one here, the 3's cancel out. We're going to be left with 4 pi r squared times our dr, or error here. So now this is what we can use to calculate our error. So then at r is equal to 21 and dr, our error, is equal to 0.05. What we do is plug it in, so we get dv is equal to, or the change or error is equal to 4 pi, is 21 squared times 0.05. Plug in this calculator, just plug this in. .05. So yeah, 277. So around 277 cm cubed. If you didn't do the linear approximation method, you would have to do, well, delta v is equal to you could go v of, let's say, 21.05 minus v of 21, and then plug this in the calculator. That's a bit harder. And this one you could just do it directly like this. But then, and this 277, this seems like it's a lot, but it's not too much if you compare it to the full volume. So if you compared the relative error, you'll just have, let's say, change in v divided by v. This is equal to, well, it's roughly equal to, let's say, dv over, that's the linear approximation one, over v. This just equals to, just plug in the formula, just be quicker instead of having to plug everything in. 4r squared dr divided by 4 over 3 pi r cubed. Now the pi's cancel, the 4's cancel, we're just left with 3dr over r. So then you plug this in the calculator, we get 3 times 0.05 divided by 21. This equals, yeah, 0.007. And then times that by 100, yeah, basically 0.007. Or if we times by 100%, we get, yeah, 0.7% of the difference. So basically it's 0.7% of the volume, which is very, very little. And as you can see, yeah, this method's much easier, because if you were actually to plug this into the calculator, you would get roughly 277 as well. I tried this before, but it's just a much bigger hassle, and sometimes you, like I said before, if the equations are too complex, you can't actually solve for it. You actually have to do this. Well, that's all for today. Hopefully you learned, and stay tuned for another math easy solution.